In the previous example, I used one-way ANOVA to compare gender, males to females, and that really didn't use ANOVA to its full potential. The one-way ANOVA in this case is capable of doing more than that. So let's just take a look at that again. Let's use something slightly different. Let's do a one-way ANOVA. Just for simplicity, we'll use the first three, M1 through M3, as our dependent variables. And instead of gender, let's use a three-level categorical variable. As you recall, we created one based on the total length of time that they exercised, and we categorized them into low, moderate, and high. So we can click that one over, and we can hit OK. And when we see this, we see for I exercise so I'll live longer, we had three different groups, low, moderate, and high, and we can see that the values did differ across the groups. We see that they differed across the groups for the second one, I exercise to make myself look good, and they also differed for I exercise as a way to have fun. So we had three levels, low, moderate, and high. This is saying, just for M1 here, that yep, indeed, the means seem to differ across those three levels. The problem now is that we don't know with those three levels whether the difference is between the low and moderate, between the low and high, or between the moderate and the high. So the great news with an ANOVA is it looks at all the means simultaneously. The downside is that when it does tell you something significant, you're not sure where it's actually significant. So with this, we would have to follow up, and we'd have to do an independent samples t-test. Let's just do it for M1. I exercise, so I'll live longer. And our grouping variable in this case is going to be still the category based on total amount of exercise, the length cat. And this is where I have to define my group. So low was 1 and moderate was 2 in terms of how we coded it. And I'll hit OK. And we look here, we can see that Levine's test for variance is not significant. So that means that we use the upper row. So we can say a t with 56 degrees of freedom is equal to 0.008. And that's really not significant at all. Indeed, if you take a look between low and moderate, the mean for low is 3.54 and moderate is 3.53. Not particularly surprising there. So let's follow up and do another independent samples t-test. This time, though, instead of low and moderate, we're going to compare low and high. And we'll click on that. And here we see that the mean for low is 3.54 and the mean for high is 4.12. Do they differ significantly from each other? We see here first the variances don't differ, so we're going to use the upper row. And we see a t with 75 degrees of freedom is equal to 2.52. And the p is less than 0.05, or more specifically, p is equal to 0.014. Now we do our very last possible independent sample t-test, compare means, independent sample t-test, define groups. And in this case, we're going to compare moderate, which is coded as 2, with 3, which is high. We'll hit continue and we'll go OK. And that'll pop up our last comparison. So moderate is at 3.53 and high is at 4.12. Do these two significantly differ from each other? We look at Levine's first. We see that the variances do not differ because that significance is not different. So we're going to use the upper row, and we'd say a t of 77 degrees of freedom is equal to 2.48, and the p is equal to 0.015. So the ANOVA, the one-way ANOVA, told us, yeah, you look at those three levels, low, moderate, and high. For M1, I exercised so I'll live longer. There seems to be a difference across those variables. But in order to figure out where the difference is coming from, we have to do a series of pairwise t-tests. The difference, if we go over this again, doesn't seem to be coming from low to moderate, but it does seem to be coming from low to high and also moderate to high. So that's where our significant differences are coming from.